All right, listen up, you guys. Eduardo's going to explain what he did. Eduardo, go ahead. Eduardo, go ahead.
I took n and then I multiplied it by little p to get the mean.
Yep.
For the variance.
You guys, I can't hear him.
For the variance, I took the answer that I got from the means and I multiplied it by little q to get 18.75. And then for the standard deviation, I did I forgot I had the square root for 18.75, and then I got 4.33.
Great. Keep going.
Then for b, I took.
That is a weird looking view. I'm sorry. There, go ahead.
I took n and I multiplied it by the little p, 90. And I took 90 and then I multiplied it by the little q, and I got 63. And then I did the square root of 63 to get the standard deviation. I got 7.937.
Great. So you'll notice these ones, it's not in cents, right? There's only one decimal place. So that one, just take 1 and subtract it. Right? That's a little bit easier way of finding that one. Okay. The other thing is these means and standard deviations. Well, you know what? We'll go to the next problem. I'll show you what I mean there. It's quite easier. This one, mean and variance standard deviation. So this one, the mean is going to be NP. So that's going to be 10 times 0.55. The variance is going to be NPQ. So it's going to be 5 times 0.5, 2.5. And then the sigma is going to be square root of 2.5 or, what did you guys get for that one? 1.58? Okay, yeah. That's good. All right, and then this one, what's my N and what's my P? Yep, sample of, that's my N. And then a survey found that 21% of Americans, so that's my little p. So I'm going to go, my mean is 1,000 times 0.21, 210. My variance is NPQ, so that's going to be 210 times 0.79, because here then Q is going to be 0.79. So what did you guys get for that one? 160.9. Okay, great. And then my standard deviation is going to be the square root of that. What did you guys get for that one? What was it? 8. We'll go with 9. That seems good. Please note, you guys, pay attention to this part. Mean, standard deviation, variance of this distribution has nothing to do with x. It's all about n, p, and q. So your x has nothing to do with it. So if I give you a problem and I say, find the probability that x is 2, like if you go back to this previous problem we did, right? You go back to this guy, and then at the end of this, find the probability at least 3 of them have part-time jobs, and then I say, find the mean and standard deviation of this distribution. That has nothing to do with the x is 3. The distribution is the n and p. The thing, it doesn't vary. So what's your n? 5. What's your p? 30%. It'd go off of, that's how you find your mean and standard deviation. Good? Everybody with that? Because people have had confusion about that in the past. So I wanted to make sure that was very clear. All right, we are done with chapter 5. Let's move on to chapter 6. So grab out your chapter 6 notes. And we're going to review those a little bit. our z-values, our z-scores, which are always super, super important. What's our population mean look like again? What is it? Population mean is what? Symbol? U. Population standard deviation? Sigma. Sigma with the tail. Sample mean? X bar. Sample standard deviation? Almost. S. Because remember, the Greek ones are our population. The non-Greek ones are for our sample. Don't forget parameters. If I say what's the parameter should be a population thing, like mu or sigma, right? It's going to be a Greek letter. So mu and sigma are parameters. Okay. Quiz problem 5. Yes. I do. I think they're. Oh, I'll get you some in a second.
So I'm not lost it.
Okay. So let's finish this first. I'll get that right to you in a second. So first off, as z-score represents, what does z-score check with the neighbors? Make sure you confirm you've done this on your handout. Okay, so you guys should have this, right?
It says on below.
Or just deal with it.
Yeah.
Above or below the mean. Right, so let's just say it together one last time. Ready? 1, 2, 3. A z-score represents... Okay, that works. All right. Again, it's really important that you guys know this, which is why I torture you and make you say it out loud.
Yeah.
Perfect. So z-scores again, right? How do you find the z-score? Well, this one is 3 standard deviations below the mean, so it'd have a z-score of -3. This one is 1.5 standard deviations below the mean, so it'd have a z-score of -1.5. This one is 2.35 standard deviations above the mean, so it'd have a positive z-score of 2.35. Oh, I didn't do that, did I? All right. How do you find a z-score? You find out how far it is away from the mean. You take it and you subtract the mean from it. That way, if it's above the mean, it's positive. If it's below the mean, it's negative. Then you figure out what that is in standard deviations by dividing by a standard deviation. So for a sample, it would be x bar minus, sorry, excuse me, that's wrong. X minus x bar over s. You guys have seen a bunch of times. Okay, so here for a second, let's get someone to read this one. Gabe, go ahead and read.
A set of data items is normally distributed with a mean of 240 and a standard deviation of 32. Convert 240 to a z-score.
Yep. So convert 240 to a z-score. Everybody, 15 seconds with your neighbors. Go. Does anybody else not have chapter 6 notes? All right, so here's my mean, 240. How far is 240 from the mean? It is the mean. How far is it from the mean?
0.
0. So what's its z-score? 0. Make sense? Good. So when you get that on your homework, don't be confused. All right, now we're getting into chapter 6. That was just a little bit of refresher before we hop in here. Who hasn't read yet? Angela, have you read?
I'm not.
Go ahead.
The shape and position of the normal distribution curve depend on two parameters, the mean and the standard deviation. Each normally distributed variable has its own normal distribution curve, which depends on the values of the variable's mean and standard deviation.
Right, so for a normal, it depends only upon the mean and standard deviation. The one we just did, binomial, that only depends upon n and p. This one, the things that are important are mean and standard deviation. You'll notice here the upper picture, those two have the exact same mean. They're centered at the same spot. But one is more spread out, and one is more squished together. They have different standard deviations. Standard deviation is how spread out you are, right? And if you're all squished up, then you have a smaller standard deviation. These two have the same standard deviation. They're the same shape. Everyone see that? But they have a different center. They have a different mean. So that means they're shifted one from the other one. It's just shifted, yeah, because its mean is at 0. This mean is at 2. So, but their spread outedness is the same. The same amount of being spread out. So their shape is the same, just their center, their mean is different. Good? All right, so again, shape represents sort of the amount of spread it is, and then the standard deviation is, that's your standard deviation. Sorry. Standard deviation is your shape. And where you're centered, that's your mean. This will absolutely come up on the exam. I might give you two samples that have the same distribution around the mean will have the same standard deviation. If their if their shape is still the same, how far they all are from the mean is still the same, they'll have the same mean. So, if I take these numbers and say those numbers, these top numbers here, have a mean of 7, standard deviation of 4.1, and I add 2 to every single one of them, what would be my new mean and my new standard deviation? Talk to your neighbors, what do you think? Think in the top row, I'm adding 2 to every single one of them. What's the new mean and standard deviation?
The shape is just longer.
So that's just like the step up above, just exactly like the one up above. Everything gets moved. They all get moved together. Actually, you get the 3 of you and the 3 of you. Can you guys get up here really quickly? Just come up here really fast. You 3 and you 3. Yeah, come up. Really fast. And just stand right here in a huddle. Can you make a huddle like a football player huddle?
Okay.
Okay, huddle.
How are we going to study for this?
And kind of put your arms, shelter, like, yep. And then shift that way 3 steps, that direction. Great. So their shape stayed the exact same, but their mean went from here to there. So their mean increased by 3, but their shape, their standard deviation, stayed the same. Does that make sense? You guys can go home then, thank you. Or not go home, but go back to your desks, your home desks. All right, so here, I add 2 to every single one of these. What's the mean going to be, guys? It was 7, what's it going to be now? 9. What's the standard deviation? Still 4.1. Everybody on board with that? Let me show you another visual. Here is a line. Here are a bunch of markers. One's here, one's there, there. And I take these guys. These guys have a mean and standard deviation. Everybody agree these 5 points? Yes? I'm going to grab them. And if I move them, oops, let's try it again. Why is it not moving? Oh no. And I move it, they still still have the same standard deviation. Does everyone see what I'm talking about? How far each one of them is from the mean is still the same, but their mean has jumped. It's way off to the right now, as opposed to over here, it's way off to the left. Good? Okay. Cool. Now, here's some properties of normal distributions. Ashley, go.
Normal distribution properties. The total area under the normal distribution curve represents 100% of the population. As you can see, a higher percentage of the population is in the middle, and fewer are on the edges or outskirts.
Right? So mostly in the middle, fewer as you get out to the outskirts. So most of the population is right smack dab in the middle. And then the outliers, there's fewer as you get towards the outliers, right? Also, the entire area, if you add up the entire area underneath here, this represents 100% of the population. This represents everybody in the poll, everybody in the study. So this represents everybody, 100% of the population. This represents 100% or 1. Good? So this area is 1. More properties. Felicia, go ahead. Oh, yeah.
Okay. Normal distribution properties. Normal distributions are symmetric, and you can also see the mean, median, and mode are exactly at the center. It's shaped roughly like a bell.
Great. So the mean, median, and mode are smack dab in the middle. It's symmetric. One side is the same size, same shape as the other one. And the beautiful thing about the median being in the middle is that means that half the data is here and half the data is there. So you have your mean, half of it's above, half of it's below. 50-50. Here is a table that has kind of more specifically all the little tiny pieces. We said about what percent is within one standard deviation. Do you guys remember? 68%. Technically, it's really 68.26, but about 68%, right? So that empirical rule is the about thing. Speaking of empirical rule, you should be filling this out. Empirical rule at the bottom. Approximately 68% fall within what? One standard deviation of the mean. Approximately what percent? What's the next one? 95%. Approximately 95% of all values fall within 2 standard deviations. Within 2 SD of the mean. And the last one? 99.7. Approximately 99.7 of all values fall within 3 standard deviations. So within 3 SD of the mean. You can see the pictures right here, right? 68, 95, 99.7. They're right there. Or right here. So my question to you guys is about what percent is in each shaded half? Right? So this half here, what percent is in there? What percent is in here? What percent is in here? Take 15 seconds with your neighbors and find those. All right, so what about the first one? Half of 68%, right? 34%. This one be half of 95%, so that'd be 47.5%. This one would be half of 99.7, so that would be 49.85%. About, right? Good, because it's symmetric. We did this last class, or a couple classes ago, I think. What percent of the population is above 1 standard deviation? So if you know 68% is on the inside, what percent is on the outside? 68% inside. The rest of it is on the outside. What's the rest of it? 32%. 68 inside, 32% outside. So 32% is this part plus this part makes 32%. It's symmetric. So that means this is split perfectly in half. How much is in each half? 16%. Right, so 32% divided by 2 is 16%. So 16% is in each half. Good? Yes? Do you guys want to look at that longer?
Yeah.
Just go ahead and flip the page. A little subtraction, you can get all the pieces if you wanted to. But remember, this isn't exact because this is the empirical rule. It's an approximation. So when you see on a homework or on an exam, if I say approximate or use the empirical rule or use the 68, 99, 95, 99.7 rule, that means use these numbers, which are not exact. They're approximate, right? You'll learn later the exact, what was this one? This one was really 68.26%. But if we say use the empirical rule or approximate, then you just use 68%. You guys see the difference? The word approximate means 68%. No approximate, then that would mean 68.26%. All right, so I'd have to say approximate or empirical rule for you guys to use this. Okay. Good. Let's take a look at some of these. All right, so with a little bit of subtraction and everything, I can find all these numbers. Why am I talking? I want someone else to talk. Brendan, go ahead.
For example, say the heights of all of the men in California are normally distributed with a mean of 70 inches and a standard deviation of 5 inches. The normal curve would be similar to the one below.
Right, so mean at 70, standard deviation of 5, so plus 5 plus 5 plus 5, minus 5 minus 5 minus 5. There's my normal distribution. And say I wanted to, really often, we want to know the cumulative relative frequency. In other words, we want to know how many are this much or less. What percent of men are 55 inches or shorter? What percent of men are 70 inches or taller? Right? So those are the things a lot of times people want to know. So let's find that. For example, about what percent of men in California are less than 70 inches tall? Ask your neighbors. What do you get? Here's 70 inches. So it's less than 70 inches. That's this part here. What percent, guys? 50%. About 50%. About half, right? It's symmetrical. Less than 65%. How about this then? Less than 65%. This part here. What about that? It might help you to look at this. How many standard deviations is this? Within what? Within 1. So this is what?
68.
68. So then, Haley, what'd you say it was? 16%. Why? Because it's half of 32%. Do you guys remember we just did that a second ago? Good? Everybody, should I move on? Okay. About what percent of men in California are less than 60 inches tall? Why don't you guys find that one? With your neighbors, figure this one out. And again, I would suggest you find this first, and then that will help you with the rest of it. Find the inside, and then that would be half of the outside.
And then greater would be 1 minus that. So 90, right? And then greater than 80 would be the same, less than 60.
How much is on the inside here, guys?
68.
2 standard deviations. How much is on the inside? 95%. So how much is on the outside?
2.5.
5%, and you're going to divide that in half. 5% divided by 2, you get 2.5%. How about greater than 60%? So greater than 60% means this, guys. This, all of that. There's 2 ways of finding it. Everyone find one with your neighbors. Go. Who has one way of finding it? Yep.
Okay, so you just take everything lower and subtract it, so it's 100 minus 2.5, which is 97.
Aha. She said the whole thing has to equal 100%. Do you guys see what I'm saying? The whole thing has to equal 100%. So the red part plus the blue part, less than 60 plus greater than 60 better equal 100%. So 100% minus 2.5% is 97.5%. Who has another way of finding it? Okay, that's fine. Don't worry. All right, how about greater than 80 inches? Find that. Greater than 80 inches. That's this part here. Ten seconds with your neighbors. Find it.
The same as less than 60. Obviously. Zeros inside, so if you lose a decimal.
Who knows? Who thinks they have an idea? What is it? Yeah. 2.5. Why?
Because it's the opposite of.
It's the opposite of this one,
Yeah.
right? This same shape. Less than -2 is the same as greater than +2. It's symmetric. Do you guys see that one? So take advantage of the fact that these normal distributions are symmetric. It's going to be useful for you as you do problems and things like that. So the other way of finding 60, greater than 60 inches, you could have taken this 2.5% if you kind of realized it was, and then added it to 95%. That was the other way that people found that one. Okay. Good. Now, Rosa, go ahead.
What if someone is 64 inches or 63.26 inches? We can find their z-score, but it won't be an integer. So how do we figure out what percent of people are greater or less than they are? We can make a table showing cumulative relative frequency for each height to the nearest hundredth of an inch. That would be a lot of work and only apply to this one set of data.
Right, we could do that. We could find it for like 66 inches and 66.5 inches, and we can figure out what all these things are. We could do that. It'd be a pain in the butt. It would only apply to men in California, with an average of 70 inches. So instead, what we can do is, if we convert to z-scores, we can find it, the normal distribution for z-scores, and we can apply that to any data we want, just by converting that data to a z-score. Because we know that all, if it's always less than 1 standard deviation, it's going to be this much. We can find it if it's less than 1.24 standard deviations. Less than negative 1.24 standard deviations. We can find that much. There is a table people have created to find all of those numbers, and they listed it out for you. Also, your calculator, your TI-84 calculators or 83 calculators, have all that stored in your calculator. So we're going to look at how to find these areas just by using z-scores instead. Okay. I'm going to skip that. This is how you do it. Who hasn't read yet? Andre, you haven't read yet.
How to use the calculator to find the area under the curve, the percent of population. Normal CDF gives you the area between two z-scores. You find the function normal CDF, which gives you...
When you do that, it'll give you, on the screen, it'll give you
and then you type
normal
in,
CDF parentheses. Go
then
ahead.
you type in the z-score separated by a comma, left z-score, right z-score.
Comma.
Right z-score.
Right z-score.
Okay.
Yep.
Example, to get the area between -1 and 1, normal CDF, parentheses, -1, comma 1, which will return 0.6827.
right? It should be about 68%, right? 0.6827, something more than 68%. So that's what you do. Normal CDF, and then you type in the left z-score, comma the right z-score, the lower one, comma the upper one. If you have a fancy calculator, then it might give you them separately, like where you put the lower one and you input that, and the upper one you input that one. We'll talk about that in a minute. But let's talk a little bit more about what these things do. So the first thing you should do is draw a bell curve and shade the area you want. First thing. So first thing I'm going to do is I'm going to draw a bell curve. So draw the little hill first, and then draw the line, because that's a lot easier. The line is easy to draw. And then, you guys listen up. Put a little marker right in the middle. That's where your mean is. Now, I want normal CDF of -1.14 to 999, or to the right. So, where is -1.14? Is it on the left side or the right side? Left side, it's negative. Everybody good with that? -1.14. Draw a line straight up, and I want to the right of it. So that means I'm going to shade this side over here. Or you guys might just do this. You can just do that. That's totally fine. Okay. And then I'm going to do normal CDF of -1.14. What's the z-score way over there, guys? What's the number way out that way?
10. A million.
A million. Okay, what's bigger than that?
Infinity.
Infinity. Infinity is way out there. However, any large number will do. What's your grandmother's age? What's your grandmother's age? Anybody?
83.
83? 95? That'll work. That's big enough. Honestly, your age in terms of standard deviations is big enough. Because all of you guys are over 10. That, if you go out that many standard deviations, that's huge.
It's because at 3 you're already like 99.7,
Yeah.
so at 10 you're be like 99 log 9.
Right. At 3 standard deviations, you're already at 99.7. Right? You go out another one, and holy blank, you're tiny. You go out 10, and it's nothing.
And in terms of actual numbers, then you're never going to...
Yeah, who would actually be that many standard deviations away from the mean? Nobody. Really, it's not really possible. Yeah.
So we're supposed to do this on our calculator?
Yes, I'm going to show you in just a couple
Oh,
minutes. Okay, so if I want you guys to understand the principle before I let you loose on that one, or else you will ignore the principle and you'll just focus on how to do it. So normal CDF of -1.14, comma, any large number, your age, your grandmother's age, 999, E99, anything you want. That's all good. And that will give you the area. So this means that 87.29% of the population is more than this many standard deviations away from the mean. It's more than this on this side. It's more than this amount. Good? Here's another example you might get. Probability. You might get a problem that looks like this. Find the probability that z is between 0, do you guys see z is between 0 and 2.53. That means the z-score is between 0 and 2.53. Z-score of 0 goes right here. Positive 2.53, somewhere on the positive side. So what would you do? Normal CDF of 0, 2.53. It's going to give you 0.4943. That means that 49.43% of the population lies between a z-score of 0 and 2.53. That also means that there is a 49.43% chance that if you randomly select somebody from the population, they'll have a z-score between 0 and 2.53. Did I say that right? There's, 49.43% chance. So those are all things to think about with this and what it means. Let's show you how to do it. Using a TI calculator and normal CDF. You're going to press second, vars. I think these directions are on there, aren't they? Yes, at the very bottom of your page. So now I'll show you what that means. So at the bottom of the page, this is it. So I'm going to hit second, this little blue button, And then the bars. You guys see the bars right here? And then, see the second one down is normal CDF, not normal PDF. The second one down, normal CDF. Arrow down to that one. Hit enter. Now I have normal CDF parentheses. If you have a fancy calculator, you may have lower, right? Lower and then upper, right? So if you have this one, then you just put in the lower one. So we want to do, let's do negative 999 to positive 1.2. So I'm going to put in negative. Do not use the subtraction sign for negative. You got to use this little button down here. This means negative number down here next to the enter key at the very bottom. Negative 999. If you have a fancy one, again, you put that in your lower part, comma, or if you have a fancy one, you just go arrow down to the next one, 1.2. This one, you just hit enter. If you have a fancy calculator, then you make sure that your mean is 0, and your SD, your standard deviation is 1. Mean of 0, standard deviation of 1.